Okay, thank you, Dr. Zalani. Thank you so much. And thank you, UMT and the community for IPCOETI for inviting me as a keynote speaker. So today, not for long, okay, I'll share a bit about electric current as a source of information for my patient and my research as well. Okay. So current for me is often misunderstood. Most people familiar with voltage, we know voltage, okay, but not very much with current. Most of the time when we measure current, people use multimeter, something like this, clamp meter, then they get the value of the current, but not of other information has been filtered out. Okay. And to really see the waveform of the current, we need a high sampling frequency, and that is what not feasible in most of our IoT hobby kit that we have. Some like Arduino, Raspberry Pi. Yes, you can perhaps sample a little bit fast to get the waveform, but then most of the information rely on higher sampling frequency that information lost in sampling. Okay, that is just in sampling, not in analysis yet. So today I'll share a little bit about my passion in current analysis, which most of it I learned here at University of Western Australia when I did my PhD doing current control. So usually when I in undergraduate, I take microelectronics, and then at master level, I take robotics. The thing that I'm not comfortable with is actually in power. So at PhD level, I jump into power electronics, try to control the current. Okay. Okay, I skip my Mentimeter because the time is not so much that I have. So the thing that make current more misunderstood here in Malaysia is because of our slang as well. We are using the term current to resemble electric. Okay, most of the population in Malaysia will see current as electric like this. Mati kena current means died because of electrocuted. Minah current is the term that we use to portray the woman that goes into electronic manufacturing factory when Malaysia start our industrialization. This is back in 70s and 80s. And then budak current is students that study electrical and electronic engineering. Actually, perhaps in Malaysia, only budak current understand the real current. Okay, so, okay, I skip this Mentimeter. So how does the current looks like? Okay, so actually it depends on the loads, because unlike voltage that have been generated, we give the voltage to the loads. Current depends on the load. How the loads operate will shape the current. For example, most of our large loads look sinusoidal like this. The current looks sinusoidal like this. But most of our loads is actually nonlinear. Okay, how do I say this? Because this waveform is this is three-phase nonlinear loads, but most of our loads, let's say in our house, okay, our large loads is mostly linear, like our this rice cooker, our heater. They look very sinusoidal, the current. But perhaps my audience here not so much in electrical and electronics. Most of our loads that we have now is actually nonlinear. Okay, I'll show some of it. Okay, This is two waveform of current that I captured and I give to the audience to guess what is this current. Okay, so it doesn't look sinusoidal. Okay, it's not so much, very little. Okay, and this is actually the current for CFL, our compact fluorescent lamp. Okay, brand Philip, and this is our Mr. DIY. So it's not so much different. Okay, but this is how the current looks like. Okay, and this is smaller current. Okay, smaller current, quite similar. Okay, and this is for LED lamp. Okay, 5-watt LED lamp and 5-watt LED lamp. Okay, and this one, this is the current that we not see, but the electrical system in our house, it see this every day. Okay, this is the current that we use a lot in our PDPR because this is the diode rectifier load. For example, here on my right is the technology called warp charge by OnePlus. Okay, the one that it is fast charging capability for handphone, and this is Huawei Supercharge. So it looks similar. Okay, because of what? Although the technology is different, okay, but charging technology mostly on the DC side. This current is on the AC side, so this is purely diode rectifier current. Okay, so why am I showing this? Okay, I want you to guess what signal is this. Okay, I'll be talking about this signal a lot. Okay, so put your guess. Okay, what signal is this? Put your guess in the chat section, or for my audience in live stream, just put on the comment section. Okay, we'll talk about this after this. Okay, now this is my electric vehicle. I've been using this since 2018. Okay, this is the, I think this is the first electric vehicle in Malaysia. So this is Moderna's C3. Yeah, I think this is the first road legal EV in Malaysia. Okay, so it doesn't sell well back in around 2011. Okay, but then I bought it and I changed the battery. So right now it's run on lithium-ion battery. So this is my daily vehicle, and it's only charged by a slow charger, 400 watt. Looks it's still very much diode rectifier load. Okay, everything that convert into DC. That's why now our television is in DC. Okay, our phone, our monitor, we use a lot of computers, laptop. All that is DC, and most of the time they will have current that looks like this. Okay. Okay, this is one of my final exam question actually. So I go to the lab and I put a little bit of nonlinear loads and capture them, the current in three-phase system. So this is the voltage, and the blue one is the phase current. Okay, interestingly, the neutral current. Okay, so this is the neutral current. So I put there. So the neutral current is actually very much distorted compared to the phase current. So I think this is a T5 lamp. We put a lot of T5 lamp in three-phase system, and we sample the load current and then the neutral current. So what interesting is these harmonics. Third harmonics is what been notorious in three-phase four-wire system. Okay, so this third harmonics is actually multiply in neutral. So as you can see here, okay, although this spectrum, harmonic spectrum, looks normal, actually it's not. This is just for neutral current, where you can see here the fundamental is not at 50 Hz. Okay, so the fundamental is actually at 150 Hz. That's the third harmonic. Third harmonics become the biggest portion in the neutral line. Okay, so let me see the chat. Okay, so we got gas current with no negative value, means okay, both inductive and capacitive element. Okay, that's one of the gas. Okay, and then from Kak Yam, current from DC-DC. Okay, let me show you the real current for this. This is actually current that I take from welding current. So a few years back, okay, my student is Afida Tushima. She is actually an EE student and then graduated working in oil and gas industry, and then got certified as this welding inspector. Okay, so we are trying to figure out how welding current affect the welding quality. So we know that the welding current looks like this. Okay, there's section called this arcing period. Okay, this arcing period is actually where the arc is built up between the metal that what do you say that? I don't know the welding term, okay, but it will be the one that melted on the piece, okay. So it will become a droplet later, okay, after become heated, and then when it touch the metal at the specimen itself, then it's become pinch. So at this point, it's become this short circuit period. So based on this hypothesis, okay, we try to figure out whether at seeing just the welding current, can we predict the welding quality? So that's the hypothesis. So we do the experiment like this using G-mount welding, and then we take a lot of specimen, okay, just two carbon steel plate, and then welding without any whether we want to be a good welding or bad welding, we don't really care about that. We just want to see whether the current match the welding quality. So this is some of the specimen that we have. Okay, as you can see, the bottom one looks quite bad. Okay, and then we do some visual inspection. Okay, this is done by my student and a third-party person to verify the. This is a double verified visual inspection. So you can see that this one got a problem here. Okay. And another problem there. Okay, this is just two specimens, and then we correlate, not really correlate, we try to match the welding current that we have, the blue one, okay, with the specimen. So we take the when it start and then when it's end. So actually what happened here is we change our welding current from current versus time into current versus distance. Okay, so that we can see what is the current at how the current looks like at every 1 millimeter slices of this welding quality. So what we see is the good quality welding have waveform like this, and this is consistent throughout all the specimen that we have. Okay, it looks like this. Okay, I'm not talking about the analysis yet. Okay, I'm just talking about the waveform, how it looks like. Okay, for one of the defect that is called as lack of penetration, where the bottom side, okay, or the welding, when we weld at one side, the bottom side doesn't have any penetration, so that is lack of penetration. So when lack of penetration happen, the current looks like this. Okay. Lack of fusion, okay, it looks like this. Okay, there are quite a lot of defects, but I'm not presenting all of them. Okay, excessive weld always looks like this. Okay, the shape of the current is bigger. Okay, the area under the curve is larger. Okay, so this is what excessive weld looks like. Incomplete weld looks like this. Okay, so based on this, we are trying a few analysis. When we're talking about signal analysis, you have a lot of analysis. You can do fast Fourier transform. You can extract the frequency components. You can do a very simple analysis, which is what we do, because we see here the one parameter that easy to extract, and it sort of become the determining factor for this type of defects is how many peak. Okay, how many peak. So this one is only one peak. That one is one big peak. Okay, and one smaller peak. So we calculate the peak. So this is peak count. So when we do peak count in our analysis, okay, we see that all these defects, arc strike, burn through, lack of penetration, lack of fusion, excessive weld, incomplete weld, undercut, underfill, all of this is very much different with the good welding. Okay. Unfortunately, there are two types of reference that become very similar to the good welding in terms of peak current. Okay. So not in terms of peak current, in terms of the numbers of peak in every millimeter of welding, the porosity and concave. So these two, our finding shows that these two will need further analysis to being distinguished from the good welding. But all other welding is easily being distinguished from good welding just using peak count. Peak count is very similar to our pulse, our heart rate analysis by most of our handphone. Okay. So it's a very easy type of analysis that we can do. So this is our finding. Okay. So what's next? Okay, we come to the end of the session. Okay, what's next? Now, the current analysis is application is actually limitless. A lot of things we can extract from current. Okay, you can do machine diagnostic for predictive maintenance, just like motor current signal analysis. Okay, motor current signal analysis is very similar to what I did. Okay, but then now our motor is not really an inductive motor that we just give a sinusoidal voltage. Okay, motor current signal analysis will need a few revamp. Okay, because now we are controlling the speed of the motor in different way. Okay, and we can do real time quality monitoring as a human aid. For example, this welding. Okay, just imagine the welding the machine itself. Okay, incorporate this. It's very easy to assemble actually, the shunt resistor for analysis. So just put that shunt resistor, and then we know when the some defect happen during the welding itself. So it will reduce a lot of rework on welding once you have that kind of ability in the machine itself. Okay, and then if you ask me what I predict the current analysis in the next future, okay, it will be more current will be sensed. A lot more current will be sensed. Every house will have a current sensor, okay, to monitor the usage, to tell us something more about our habits inside the house. Okay, signal processing algorithm will be a plug-and-play coding block. Because of what? A lot of current analysis cannot be done now, because once you attract the signal, once you get the signal from the current source itself to the your, let's say, Arduino or Raspberry Pi, you lost a lot of information already. Okay, so we need something in between, okay, to analyze this at real time, at fast sampling. Okay, for example, the waveform that I take just now, I show you some of the waveform. That waveform is at 2 million sample per second. Okay, when you get higher sampling rate, you get more information. Okay, for example, during my PhD, okay, I'm doing active power filter to test my digital current control. It's not just the sine wave or the wave itself, okay, but the information of the triangle inside every switching frequency. That triangle, each of that triangle is at my switching frequency 17 kilohertz. So to sample that, we need a higher sampling frequency. So I'm guessing signal processing algorithm will be available in coding block later, so that we can put our coding just like our IoT and our AI now. And then we need a lot of AI in current monitoring, because this thing happen fast. Okay, it will be similar to our watch that monitor our heartbeat. Okay, that monitor our heartbeat. So as soon as the heartbeat become irregular, okay, the watch can tell the something worth investigating. Okay, so AI will be used in current analysis a lot more. Okay, so we know when our motor become bad. Okay, our wind turbine, usually wind turbine we put close to the coastal area, so we have a lot of this corrosive, not corrosive, corrosion is as well, and oxidization. Okay, so that thing will degrade the wind turbine, and then we can see from the current that something is going on, something worth investigate. Okay, this is what my prediction will be. So as conclusion, there is no conclusion. Okay, what I present is only potential for further exploration. Okay, so for all postgraduate at this conference, all the best. You in your study now in pandemic area. So I wish you all the best. That's all, Zalani. Thank you.